So, welcome back to our discussion on understanding deformation in a fluid. And what we saw when we were looking at deformation in a fluid is that the deformation in a fluid understood in terms of what is the relative velocity between two neighboring points. So, if you have 2 points that are separated by a distance that is given by the separation vector r, then this change in velocity can be split in terms of a symmetric part and an anti-symmetric part, where the symmetric part is related to the symmetric component of the velocity gradient and the anti-symmetric part is related to the anti-symmetric component of the velocity gradient. So, this is basically using the idea that for any velocity gradient, you could actually write the velocity gradient in terms of a part that is symmetric and a part which is anti-symmetric. And the purpose of doing this is we want to get a feel for what happens to the fluid in terms of its deformation. Can we decompose what is going on? So, Eij has a property that is Eji and Rij has a property that it is minus Rji. So, we saw for the symmetric part that this object which is the symmetric component can be written in terms of a gradient of a scalar function, and that scalar function is expressed in terms of the rate of strain tensor. So, E is the rate of strain tensor, and by going to a coordinate system that is aligned with the principal axis of the rate of strain tensor, we are able to gather information regarding how does a material element get deformed under the action of the straining. So, this gave us a picture that the material element can actually get stretched or compressed, and today we are going to focus on what goes on regarding the anti-symmetric part. So, the anti-symmetric part is related to the rotation tensor. The rotation tensor is given in the following way: dou u dou rj minus dou uj dou ri, half of that. Now, as you remember that a second order anti-symmetric tensor, if I am trying to write out rij, so in a matrix form, this will have 0 diagonal elements because it is anti-symmetric. So, it cannot have diagonal elements. The off diagonal elements, if I write them as R11, R12, then this would be R13 and this would be R23. This would be minus R11, this would be minus R13 and this would be minus R23, which tells us that any antisymmetric tensor can be expressed in terms of an object that has 3 components, because you can see that to define this antisymmetric tensor, I only need 3 entries, I do not need more than 3 entries. For a symmetric tensor, which was the rate of strain tensor, there I would have the diagonal elements E11, E22, E33, then E12, E13, E23, and that is it, because the other diagonal elements are going to be exactly the same. So, you need 6 entities or 6 entries to define a symmetric tensor, whereas you need 3 for an antisymmetric tensor. If you do not say anything further, if you are not giving any further constraint on this object, then you need only 3 for an antisymmetric tensor, and the antisymmetric tensor that we have here is a rotation tensor. So, when you have this, then this is true for any antisymmetric tensor, that an antisymmetric tensor can be expressed in terms of a pseudo vector. So, any antisymmetric tensor you would be able to express it in terms of a pseudo vector. In general, for any antisymmetric tensor, you could also write it in this manner: epsilon ijk with some pseudo vector that is b. Here, this omega that we have here has a very precise definition. So, which is why with the factor of minus half it appears here. So, omega is curl of the velocity. So, if you look at individual components, so let us say if you wait, sorry, this should have been R12. R11 will always be 0. So, it should be R12. So, let us say if you take R12, R12 is half dou U1 dou R2. Indices 1 and 2 are basically the directions, minus dou U2 dou R1. Now, curl of U, if I were to write down the third component of curl of U. So, curl of U, you will have the direction 1, direction 2, direction 3, dou R1, dou R2, dou R3, U1, U2, U3. So, if I want to write down the third component of curl of U, the third component of curl of U would be dou U2 dou R1 minus dou U1 dou R2. And just to remind again, R12 is half dou U1 dou R2 minus dou U2 dou R1. So, if I define vorticity, which is a new quantity that you are encountering, the curl of U, this object is known as vorticity. So, we have not formally understood what this means, but if I just give it a label right now, that curl of the velocity field is this object vorticity. So, we will encounter this a little bit more going forward. So, it is the third component of omega. So, you can see that R12 is minus half omega 3, right. If you were to now ask what is, so the relation is Rij is minus half epsilon ij k omega k, where omega is curl of U. So, now if you were to let us say pick R23, so R23 would be dou U2 dou R3 minus dou U3 dou R2 with a factor of half. Now, what is omega's one component? We have it right ahead of us, dou U3 dou R2 minus dou U2 dou R3. And we see that R23 is minus half of omega 1. The pending one, which is R13, is half dou U1 dou R3 dou U3 dou R1. And if I find what is omega 2 would be dou U1 dou R3 minus dou U3 dou R1. So, on comparison, you have R13 is plus half omega 2. So, the plus sign, as you can see, that if you write it as R13, this becomes minus half epsilon 13 k omega k. And from the property of permutation symbol, the only non-zero entity of epsilon 13 k is 132, because 131, 133, all of them would be 0. K can basically run over 1, 2, 3, but it cannot take the other values because it would basically give you the 0 answer. So, the only non-zero value is epsilon I32, and then this is only allowed to be omega 2. So, I have R13 as minus half epsilon 132 omega 2. Now, what is epsilon 132? If you forget ever, just do this and you see it goes in the anticyclic sense. So, if it goes in the anticyclic sense, the permutation symbol will pick up a negative sign, which is why it becomes plus. So, this is quite useful, that you have learned that the rotation tensor, even though we are calling it as a tensor, the rotation tensor and this is in general true irrespective of what we are studying right now, that any antisymmetric tensor can be expressed in terms of a pseudo vector. Pseudo vector is what we defined earlier, is something that is careful about how you do the reflection operation. When you do a reflection operation, it picks up a change in sign, which is not the same for a true vector. So, things like angular velocity, things of like torque, angular momentum, and here we are basically encountering an object that is curl of a velocity field. So, velocity field is, or velocity is a true vector. The moment you take a curl, immediately you are considering a handedness. Without deciding a handedness, you cannot define what way does curl of u point. So, if u was defined, then how would curl be? So, for to say that, you need to define what kind of a right hand or a left hand coordinate system you are choosing, and that is the reason that object curl of u is a pseudo vector. So, here that antisymmetric tensor that you have, Rij, is related to a pseudo vector, which is here the curl of velocity field. Now, if you want to invert this, if I want to invert and write omega in terms of Rij, how do I do that? So, I have Rij is minus half epsilon ijk omega k. I want to write omega in terms of R. Now, if it was just a matrix kind of an operation, you know how to do inverse, but here you will see that it gets simpler even when the object is no longer an order 2 tensor. Here you have an order 3 tensor to play with. So, tensor algebra here comes to our help. So, what I will do here, I will multiply both sides by a tensor that is the permutation symbol epsilon ijm. So, I do the same thing here, epsilon ijm. Now, here on the right hand side, I have to do this calculation, epsilon ijk epsilon ijm times omega k. Now, how do I find this? So, we have learnt that epsilon ijk epsilon kmn is delta im delta jn delta in delta jm. We saw this relation, right, that this object is a order 4 tensor, it is order 4 isotropic, which means it will be combinations of the order 2 tensors, and then you can work your way through the coefficients and find this. So, this is a very useful identity, taking a dot product of the epsilon or the permutation symbols and writing it in terms of the Kronecker delta or the antitensor. Now, in this you can make this further simpler. If I now say that j is equal to m, so epsilon imk is epsilon kmn. The only change I need to do is I need to change wherever I have a j to and m, and this becomes mm. So, the first term becomes delta in minus delta in, and this is 3. Which hopefully all are right. So, delta im. So, I have replaced j with m, which means here I would replace j with m, here I would replace j with m, delta mm is 3, and that gives me minus 2 delta n. So, the relation that I had here, which was written as epsilon ijm, so epsilon ijm rij is minus half epsilon ijm epsilon epsilon ijk omega k. So, now you can try to use what you have here. Now, this is, you have to just keep track of what is free and what is repeated. So, if you just want to write it in this exact form, what I can do is I can take I. So, this is minus mik kmn, and then I can write this with I once more, this becomes mki kmn. So if I want it exactly in that form, so it becomes KMI KMN. I'm just playing around with swapping the indices and this is what I get. So once I plug that in, so I have now, so this is equal to minus 2 delta IN, right. So if I apply it here, I have minus half. So the free indices here are I and N, whereas here the free indices are M and K. In this relation, the free indices are M and K. I and J are the repeated indices. So when you just apply that, it becomes delta Km omega K, which is K in omega gets switched. As I said, the Kronecker delta, whenever it operates or dots with some quantity, it is going to replace the repeated index with the free index. So this becomes omega m. So omega m is epsilon ijm rij. So we have just inverted this relation. If you ever want to actually write the curl of u, which is a vector, in terms of the antisymmetric tensor, this is what it will be. So this was going through back and forth trying to say that the antisymmetric tensor can be expressed in terms of a pseudo vector. Now how does that, help us in getting a physical picture of what is going on? So what was, we should not lose track where we started off from. So what we started out from is to say that the relative velocity between 2 points, it has an antisymmetric component which is expressed in this manner. And through this exercise we saw that the antisymmetric tensor can be expressed in terms of a pseudo vector, which is the vorticity, that is defined as the curl of the velocity field. So if I plug it here, this becomes minus half epsilon ijk omega k r. Now I will just switch the indices j and k. So the moment I do a switch, epsilon ijk is minus I kj, right. That is again using the property. Every time you switch two indices in the permutation symbol, it picks up a negative sign. So epsilon ijk is minus epsilon ikj times omega k rj. So the antisymmetric part is half, sorry, let's write it with the epsilon first, epsilon ikj half omega k rj. Now this is nothing but omega by 2 cross r, the ith component. So when you have 2 points that are separated by a distance that is r, then there is the relative velocity component, the antisymmetric part, which is related to the local or the value of what we are calling as the vorticity, the curl of velocity. And this, if you remember from your expression of how velocity is related, that velocity between 2 points would be related to an angular velocity as omega cross r. So if 2 points on a rigid body were to actually, if the rigid body was spinning with an angular velocity omega, the relative velocity between the 2 points. So I have a point A, I have a point B. So imagine that you have a disk which is spinning with an angular velocity omega, and if these were the 2 points, the relative velocity between those 2 points would be omega cross r. So what this tells us, this entire exercise tells us that the antisymmetric part of the velocity gradient is responsible for a spin, where the angular velocity is half of curl of u locally. That is a very important point. I am emphasizing the point locally because we are doing all of this assuming the 2 points to be infinitesimally close to each other. So if you are considering 2 points to be very close to each other and trying to understand what is the relative motion, one part of the relative motion is a spinning motion, and how fast does it spin depends on what is the local vorticity. What is the vorticity, which is right now just defined mathematically as curl of velocity? What is the local vorticity at that particular point. So curl of u, now you can use this in the converse statement, that curl of u is a measure of the local angular velocity. So in a fluid, locally fluid particles can spin. To understand what it means locally, you are thinking of points that are infinitesimally apart. So when you are thinking of 2 points, these 2 points are separated by a small distance r. They have a relative velocity, which I am saying is du. Du has a symmetric part and an antisymmetric part. We understood a little bit of what was the symmetric part doing. It was responsible that if these 2 points were being stretched or compressed, and the direction of stretching and direction of compression depends on the local rate of strain tensor that is there. What the antisymmetric part does is, it makes one point rotate with respect to the other point. And how fast does it rotate is given by the local value of the vorticity, or it is precisely half of the local vorticity. So vorticity, which is a quantity that we have already going to go through in some detail later, you are already seeing that from a kinematics point of view, vorticity is a measure of your local rotation. That point local is very important. When we go through and define vorticity, we will actually see that what a fluid parcel does globally. Globally means that if you put a small dust particle in a flow and you track how that dust particle goes around in the flow, that is not necessarily going to give you a measure of the local rotation. If you were to consider that there was a small cross that you have drawn in the fluid, place 2 small sticks, and based on our assumptions, those sticks are infinitesimally small and they don't disturb the fluid, so they are passively responding to the flow field. So the center of mass of this can go around in a circle. That is one sense of what you think in terms of making an orbital motion. The other is, as it goes around, sorry, this should always be, so as it goes around, it can always do this, in which case the center of mass is making a full revolution. But those 2 crosshairs that you have drawn, those 2 lines that you have, they don't have any spin. Whereas you can have another configuration where this crosshair, as you can see, has a local spin. So even here it makes a full circuit, but while making that circuit, it also experiences a local spin. There is a clockwise spin that is there in the problem. So it doesn't matter what path the center of mass makes. What vorticity tells you is what is the local angular velocity. So distinguishing the two is quite important. We have basically learnt about streamlines. So streamlines, if their streamlines are basically straight or they are curvilinear, that is not necessarily going to give you a feel of what is your vorticity. So this, by trying to understand the rotation tensor, we have actually encountered and learnt about something which is very fundamental to fluid mechanics, which is the idea of vorticity. Now you could also do this physical picture trying to see why the vorticity is a measure of your local angular velocity. We discussed this through the rotation tensor. One way to do this is, if you consider a small spherical element, again the same assumption that this object is infinitesimal in size, and you try to ask the question that what would be the angular momentum for this particular element. If you try to calculate that, I want to find out that what is the angular momentum for this particular element. So if you use the idea that this is an object where the velocity is distributed over the size of this sphere, so then the angular element would be epsilon ijk rj uk rho dv. dv is this volume. So I consider a material volume and I know that the velocity varies inside that volume. Now integrating, so this epsilon ijk rj omega k uk gives you what is the angular momentum per unit mass, and then integrating rho dv over it basically gives me the total angular momentum of that small blob that I have. Now if I say that the size of the blob is very small, so the volume that I am looking at is infinitesimal in size, in which case I can do an expansion of uk about the center. So if I just zoom this in, I have this blob now, I have zoomed it in. So let's say this is the center, I define it as the origin. So at any point I am basically going to calculate, so let's say this is the velocity here, this is the separation vector. So you try to calculate what is the angular momentum by integrating this over all points inside that volume that you have chosen. Now if the size of this object, size of this material volume was small, I can do a Taylor series expansion of the velocity at any point in terms of the velocity at the origin plus the velocity gradient at the origin. This is what we started out with, right, by defining an idea of a velocity gradient. Obviously there are higher order terms that will be there. Those higher order terms would be quadratic or nonlinear in the separation. So if I just say that r is very small and the size of the volume that I am considering is very small, I can just start with this approximation. So if I write this out, I will have rj uk about the origin, and I should be using, so this is where you see in tensors you have to be a little careful. If I would have used m here, I would have made a mistake because I would have two pairs of repeated indices having the same notation. So the moment I am using here, I just need to be careful that I have j here for repeated. So I am trying to choose a different letter here. So this is something which you just pay a little attention to when you are doing these kind of exercises. Now if I write this term by term, so epsilon ijk rj uk about the center of the sphere, in this case if I am thinking of it like a sphere, plus epsilon ijk rj rm dou uk dou rm rho dv. Now these are all constants, they are evaluated at the center of the sphere. So I will take it out. So I have uk0 epsilon ijk rj, well let me just do this here itself. So this is the angular momentum due to the translation of that object. uk of 0 is with the velocity with which that volume is moving. So the translation of an object about its center of mass will not create an angular momentum about its center of mass. So this is going to be 0. Just rigidly translating an object will not create an angular momentum about its origin. The next part is epsilon ijk dou uk dou rm 0 rho rj rm dv. Now this is something which you might have seen before, integrating the density of an object with the separation vector. This is what is known as the mass moment of inertia tensor. Rho r square dv, if you have done it for trying to find it about a particular axis, then this will basically be, so when the moment of inertia, you would have earlier learnt it like a quantity that has only one component, but it is actually a tensorial component. So when you calculate the moment of inertia, you will have terms like rho r1 dv. So this would be I11. Similarly, I13 would be rho r1 r3 dv. So this is the moment of inertia tensor for this particular object. So L1 epsilon ijk dou uk dou Rm 0, this becomes I j m. Now, we are considering a sphere here. We choose an object, we are free to choose what we want. So, the object that we have decided for which we are trying to do this exercise is a spherical object. So, it is an isotropic object, which means when I am trying to calculate the moment of inertia tensor for this, we know that moment of inertia tensor should also be isotropic. And by now we have done this enough number of times to know that if this has to be isotropic, then it only has one possibility, which is being proportional to the Kronecker delta or the anti-tensor. So, we are almost done now. So, we have ijk dou uk dou rm. I am going to drop this 0. We understand this is about the origin. I delta jm. The last bit, so epsilon ijk I. Now, the identity tensor acts on the velocity gradient, and I can now write this as dou uk dou rj. Now, doing the decomposition that we have been doing so far, the velocity gradient can be written as ekj plus rkj, the symmetric part and the anti-symmetric part. Now, if you look at the first term, that is ijk double dotted with E, that is the first term. This object is anti-symmetric about j and k. Ekj, however, is symmetric about k and j. And we have learnt that when we do this exercise of a double contraction of an anti-symmetric tensor with a symmetric tensor, the eventual product would be 0. So, the angular momentum for that differential sphere that we have, the infinitesimally sized sphere that we have, is I ijk r kj. And now, we have already done this, saying this anti-symmetric tensor can be written as and I am not going to repeat this once more, we have gone through this. So, here I should have half I omega I. Now, if you map this to what you know for a spherical particle that is actually spinning with an angular velocity omega, then the angular momentum is I omega, which again tells you the same thing, that the local angular velocity should be half of the local vorticity. So, here I have, there should be a factor of half that I have missed here. So, factor of half, which then gives you Li is half I omega I. So, this now completes our picture. The picture is, if I have 2 points that are separated by a distance r, and I am trying to find out what is the change in the velocity between those 2 points, that change in velocity can be expressed in terms of, let us say this point is at x. So, it can be expressed in terms of the velocity at that point x plus, so I am trying to find what is the velocity at some other point. So, either you write in terms of increment, or if you try to write the velocity in terms of, so this is, let's say this is the point A and this is the point B. So the velocity at point B will be expressed in terms of the velocity at point A, and then we arrive at the symmetric part, which is half Rj Rk Ejk, and the anti-symmetric part, which is half epsilon Ijk omega j Rk. This is just a uniform translation. So about a point A, if I want to find out the velocity of any neighboring point, it would be related by the velocity at point A, which is the uniform translation part, and then I have these other two pieces. Now what are these two pieces? The first one is the part that comes from the rate of strain tensor. Now what I will do here, I will just take this a little further and write this Rj Rk epsilon Jk. I could write this as half Rj Rk epsilon Jk plus half Rj Rj epsilon Ii minus half Rj Rj epsilon Ii. So I just write the first term as Rj Rj epsilon Ii, and the second term I can write as Rj Rk epsilon Jk minus 1/3 epsilon Ii delta Jk. So let's so this, okay, there is, this should be what I've subtracted. I will write it as, so you will see why this factor of 1/6 comes. So this, now why I am doing this kind of a splitting, I just added 1/6 Rj Rj Eii minus 1/6 Rj Rj Eii. So now if I rearrange it and then combine these two, this is what I will get. Now what's the purpose of doing this? If you see the second term Ejk, Ejk minus 1/3 Eii delta Jk, if you take the trace of this, the trace of this object is going to be trace of Ejk minus 1/3 Eii trace of delta Jk. The trace acting on the entire thing can be written as trace acting on the individual components. So what is trace of Ejk? Trace of Ejk is Ejj or Ekk, and here this is minus 1/3 Eii, and trace of Jk is 3, which is Ejj minus Eii. There is nothing special about Ejj with j or Eii with I, which is 0, which means this part is traceless and the trace have been separated out. Now why is this, why am I doing this exercise? So I said that if the velocity field was divergence free, then material volumes are preserved. The counter statement would be that if you have a velocity field which is not divergence free, so if divergence of u was not equal to 0, or trace of the rate of strain tensor was not equal to 0, the one and the same statement, then volume elements are not going to preserve. The material volume will not be preserved. If you remember, divergence of u, we wrote it as 1 by j dj dt, this being the transformation that is going from one to the other coordinate system. In terms of volume, material volume, it's the same statement, because you remember j was giving us the mapping from an initial volume to a final volume. I considered an initial volume V0 and it got mapped to a final volume. J was the transformation that gave us that Jacobian that was there. So, the divergence of u is related to the rate of change of material volume. So, if divergence of u was not 0, material volume would not be preserved. So, what we have done now is, by writing this object half Rj Rk Ejk, we have written this right now as dou dou Ri 1/6 Rj Rj Ekk plus dou dou Ri half Rk Rl Ekl minus 1/3 Ei delta Kl. This part is isotropic expansion or contraction. If you just consider, let us say, a spherical volume, does it expand isotropically? That means that by the same amount in all directions, or does it contract isotropically? So, if the velocity gradient was not divergence free, there would be an isotropic expansion and contraction, which means volume is not preserved. If volume had to be preserved, you cannot have isotropic expansion or contraction, right? If it expands in one direction, it has to contract in another direction if volume has to be preserved. So, this part is actually taking out what is the isotropic component of your straining, and this part is the straining component associated with no change in volume. So, the velocity has a uniform translation, has an isotropic expansion part from the rate of strain tensor, has a straining part that is not related to change of volume, and finally, it has a part that is related to a solid body rotation. So, we see that the deformation in a fluid element is can be decomposed into these four pieces. The first one is not really a deformation, it is just a uniform translation. The last one is also not really truly a deformation, it is a rigid body rotation. The deformation part is actually coming from this rate of strain tensor. But then the velocity gradient also has this one piece of involved in it, which is the part that comes from vorticity that tells us how much it is spinning. So, we will try out few problems and actually see if we can get a feel for what is going on in this problem. So, let us take a velocity gradient which we have done couple of times. So, I will take a velocity gradient which we worked out in class before. We did the streamline calculation. So, if you remember, in this particular problem, when you did the streamlines were x1, x2 is equal to constant. They were rectangular hyperbolas. So, now the question is that if you have a material element that is drawn here, how would the material element actually get deformed? What would be the deformation of this square patch or rectangular patch? Now, we already know that if I write this thing out, the velocity, the velocity is going to, if I write in terms of a velocity gradient, the velocity gradient here would have a component that would be 1, 0, 0, minus 1. This is my velocity gradient, right. Now, the rate of strain tensor associated with this will be half. So, what I need to do for the rate of strain tensor is take the velocity gradient and add the transpose. So, that would be 1, 0, 0, minus 1 plus half. The transpose will also be the same, which means in this case the rotation tensor is the off diagonal elements are 0, the only diagonal elements, which means the rotation tensor is 0, the entire thing is the rate of strain tensor. So, now if you take this rate of strain tensor, what you realize is that at any particular point, if I want to find out what is happening between the two neighbors. So, let us say I choose a point which is A and I choose a point B, two end of that rectangle. So, the point velocity at B, if they were separated by a small distance, the velocity at B is going to be related to velocity at A, but that is not all about it. There is going to be a contribution that will come from the straining part. So, the straining part here tells me that I am going to actually experience, should I get an isotropic expansion or contraction. So, if you check the trace of E, the trace of E is 0, which means there will not be any isotropic expansion or contraction. So, there is going to be a stretching and compression without any change in volume. So, this rectangular patch is going to stretch. Now, what would be the direction of stretch? To find the direction of stretch, we need to find what are the principal axes for this. And for this particular rate of strain tensor, which is 1, 0, 0, 0, 1, 0, 0, minus 1, the principal axis would be the x1 axis and the x2 axis. If you calculate the eigenvalues would be positive along x1 and it would be negative along x2, which means this is going to have a translation because the velocity at A is not. So, velocity at B is going to move, but it is also going to get thinner. So, it is going to go slightly down and going to get stretched. So, if you consider, let us say here a square patch, the square patch at the origin is going to become a thin rectangle which is pulled along the x2 axis. You can keep repeating this. You can take a velocity which is u1 equals x2, u2 equals 0. Fairly simple velocity field. If you write down the velocity gradient, so dou ui, dou xj, if you write down the components, dou u1, dou x1 is 0, dou u1, dou x2 is 1, dou u2, dou x1 is 0, dou u2, dou x2 is 0. Now, if you were to write down the symmetric and anti-symmetric part, then there is a symmetric part, because if I add this to its transpose, then I am going to get 0. The transpose of this would be 0, 0, 1, 0. So, I will have 1 and the other component would also be 1. So, half in the 1, 2 component and this other part would be half in the 2, 1 component. That is the symmetric part. For the anti-symmetric part, diagonal continues to remain 0 and I will have 1 minus 1, right. So, this is my rate of strain tensor, this is my rotation tensor. Now, if you try to find what will happen to a fluid element, if you focus on the rate of strain tensor, the rate of strain tensor here, again if you try calculating the eigenvalues and eigenvectors, you will find that the eigenvectors are 1, 1 and minus 1, 1. So, 1, 1 will be this axis at 45 degree. Minus 1, 1 will be this one. And if you calculate the eigenvalues for this, again, I mean, I am showing this quite quickly, but you can just take this matrix, find the eigenvalues and eigenvectors. The eigenvalues associated with the 1, 1 eigenvector would be positive, and the eigenvalue associated with the minus 1 direction will be negative, which means this is a direction along which you have stretching that is going on. This is a direction along which a compression that is going on. So, the rate of strain tensor associated with this velocity field will have fluid elements basically being drawn and stretched along a 45 degree axis and being pulled inside along a 145 degree axis. The rotation tensor here, if you calculate what would be the vorticity for this particular problem from this particular rotation tensor, you would see a rigid body motion that gives you a rotation in the clockwise sense from this. Now, this if you contrast with what you learned from the streamline exercise, when you did a streamline for this problem, the streamlines for this particular problem were lines of constant x2, which means all your streamlines are straight lines. This is what your streamlines will look like for this flow. So, just looking at the streamline, it is not obvious the amount of deformation that is going on. So, as you can see that a fluid parcel is going to get rotated in the clockwise direction. It is also going to experience a stretching motion at a 45 degree angle. So, there is going to be a certain amount of stretching. The principal axis is 45 degree and the 145 degree is which is perpendicular to that particular direction. So, this you can build for various kinds of flows and try to get a feel for what is going on. So, obviously, for the purpose of doing this in the lecture, I have chosen velocity fields which are linear, u1 equals x1, u1 equals x2, those kind of things where you can do this quickly. But if you have a more complicated flow field, you can locally zoom in the flow field at a particular point and try to get local information regarding what deformation is going on. So, in general, if you let us say you have a very complicated flow. So, I am drawing streamline structures which are like arrays of cells where the flow basically moves around in various kinds of cellular form. So, it goes up, comes down. Right. Now, this is a very complicated flow field that you have, right. I mean, there is no particular reason to expect the flow field will depend linearly on the coordinate. But if you were to zoom into different regions, so let us say I zoom into this particular point and I blow this up. Here you can see that what is happening is in that particular neighborhood, the fluid elements are basically getting pulled up and they are getting drawn in. So, if you plot the velocity gradient and then the rate of strain tensor, in these places you are going to observe that you have high straining that is going on. Whereas, if you were to zoom into somewhere here and look at the flow is going to look like everything goes around in circular tracks. So, you will find that the straining part is very low there, it is entirely dominated by rotation. Okay. So, that is the part regarding deformation, because deformation will play a big role when we will next try to use deformation to build constitutive relations. Because in fluid mechanics the part where, or rather in continuum mechanics, the part which is always the challenging part is relating the internal response of the medium to its deformation. Now, before we do that, we need to understand a little bit about deformation. That now that you have got a feel for deformation, that there is a straining component, there is a rotation component, the next thing we will later do when we will try to understand the deformation, do both of these contribute to the internal response? Will the translation part have a role in the internal response? Will the rigid body part have a role in the response, or will it just be the straining part that will have a response? So, this is what will come up next. Okay.